Wukash is also very interested in this kind of thing. And even when I called Wukash after I had this meeting with Richard, and Wukash was kind of had a combination, showed a combination of both eagerness and also kind of anger that these things hadn't even been brought up, sooner. Because I think when Wukash originally applied to the summer school, he was interested in this kind of thing, and he had even hinted briefly at the notion of starting to make spatializations and to consider analytic treatments, which I imagine we're going to encounter as we're trying to consider limits of graphs, et cetera, et cetera, et cetera. So Wukash, that's why Wukash, if you're wondering why Wukash here, no one wonders that. Everyone is always happy that Wukash is around. But if you're wondering in particular why the Langlands guy is here, is because Wukash is an interdisciplinary fellow, and he's interested in this too. So without further ado, Richard, tell us about what you've done so far, ideas you have, results you produced. I know you have notebooks to share, so let's jump in. Let's start talking about the research.
All right. Yes. So as you mentioned, we want to sort of geometrize these graphs or turn them into some kind of continuously deformable structure to make them amenable to the this space of things. Sorry, I get a little nervous on the stream, which is weird because I stream myself. So anyway, so Moduli spaces, right? The approach of graphons, this function on the unit square, which will give us a sort of generative model of graphs, and that sort of leads to the problem of graphon estimation. So given a causal graph, we have to, or given some sort of samples from it, we have to try and estimate the graphon. And the literature is quite, the techniques seem to be quite favorable. They sort of favor the dense case. And unfortunately, we don't live in the dense case like a fully connected graph is n squared edges for n vertices. So if you scale sort of sub-quadratically or whatever, then you're in the sparse regime, and we are very, very sub-quadratic because we have kind of layers in our causal graphs normally. I'm sure we could come up with a case which is dense, but the majority that I've seen are sparse.
Well, by definition, DAGs have to be they have to be in that sparse regime, right?
Not strictly speaking, by virtue of being a DAG. It's more that the way in which our causal graphs, the way in which new states are always being generated, you're always kind of like, or the tendency is that we're sort of making more room to explore in the causal graph, and we tend not to visit previous states. The tendency is not. I mean, we will, of course, but we're also sort of expanding our state space as we grow larger structures, and that gives more sort of wiggle room. Anyway, but yeah, the initial experiments actually were inspired by some ideas from Wukash. So I'll share my screen and go through. And I've actually taken it, and we had lots of discussions about, using methods for estimating these graphons, trying to embed samples of causal graphs. Today I was looking at the these variational graph autoencoders, so in that idea we would be using the latent space of this machine learning method as the Moduli space in a sense, and that was an idea we had brought up last time.
Yes.
But anyway, let me share because I will have an easier time. So I'm going to share screen, and there we go. There, and I want to see just quickly if my computation has finished. It hasn't. So we'll go back to there. All right. So this idea was not on causal graphs, but let's try and look at something like a curved manifold, simulating samples on it, and we get things like this or things like this, and these are just changing the curvature equation from like an x cubed something to what, just changing the expression here, and we end up with and lower down I take more samples. We had looked at this one before. And these are kind of
for
interesting functions.
For people who aren't following it fast enough, these are just array plots of adjacency matrices of the graphs, just in case you got lost in the code, just so people know. Yep.
Cool. Yeah.
Yeah.
And the idea is to take those adjacency matrices and sort of turn them into a function in x and y, or s and t, on the 0-1 interval.
Yeah.
And you can think of that as an infinite matrix, which has gone out to infinite extent, and now we can sample any real number in that space and end up with the sort of connection probability between those two edges. So the thing to do, or the experiment to do now, is to see if we can sort of parameterize these functions in terms of some coefficients or exponents in these curvature equations. That was an idea that I do want to continue exploring, but the utility of that is debatable, because we really want to deal with the computational objects, which I'm just going through. So let me just find the other one. So I don't want to miss any because I have 7 up in here. But the computational objects are much more subtle beast than those manifolds, and we end up with a lot of very intricate structure, and a lot of the time a lot of self-similar structure. And what I have noticed is that, and so this is not disagreeing with your point that we should disregard the computational abstraction, but what I noticed, and it's kind of obvious, that Nick has made the point, a very good point, about how Turing machines have a very kind of predictable causal graph. But if we look at something like string substitution, cellular automata, or Wolfram models, all of their causal graphs look very different. But one could imagine that they can all be living in these sort of separate islands in the moduli space. I'll come back to that point later. But
that would be right. That's a very interesting point. And I'll just to say something about that. We encounter this actually sometimes when students pick particular summer school projects. I mean, I remember this came up. I remember when Felipe, who was a summer school student, had a project over the summer. Jonathan was pointing out that there are behaviors for multi-way Turing machines that are kind of quite predictable and even limited, and you would have to kind of modify that Turing machine. I think maybe it was in sorry, I don't remember the details of the project on what you can do. I mean, maybe if you include things like blanks in the string rewrite system, you get going to take, for instance, entries on opposite sides of the string and do some rewriting. Maybe with blanks it can be different, but the point is that formal systems have constraints on the positions, how you actually execute rewriting on them, and those could some sense on a moduli space, which would be very cool.
Actually, the way in which we force Wolfram models to have no disjoint vertices is another example of that restriction. I mean, I played around in my own implementation where you could have disjoint portions of a rule, but what that means is if you have a match, now this vertex can match anywhere in the universe, which is kind of weird. So do you know what I mean? So you can match a structure, but then you can have another vertex or sort of group of vertices which now can freely match anywhere. Anyway, but I guess it's a good thing that we have that restriction of having like a sort of fully connected left-hand side, right-hand side rule. Anyway, so, and then there was some other things I was looking at, which is the sort of degree distributions. And yeah, these have interesting, like this one looks like a mixture of Gaussians. This one looks more like a gamma function. Those are just observations, not hugely relevant. And let me just see, manifold sprinkling was one that we looked at. Curved space.
Well, I do have a question actually. Could we go back to that third notebook that you showed?
Yeah, this one here.
So, okay, so one.
Yeah.
Well, I was just going to say, I mean, as a kind of informal comment, I've seen examples of graphons where I've seen what is a graphon, and usually you can tell that the adjacency matrix exhibit some behavior that kind of scales to a limit, and you can kind of show it, like be it it has some obviously symmetrical behavior, and it scales, and then you can show it smoothly, or it seems random and ends up in the limit being basically gray.
Yeah, and this is why the
What?
sparse the sparse models, some do have a kind of fine
Yeah.
structure, but they apply techniques which are, I mean, they're not going to capture the richness, the subtle sort of fine structure that we're seeing in these things. And this is even just for string rewrite systems on very basic rules. So one avenue I looked at was this thing called Kronecker graphs, because if we have sort of self-similarity, one sort of way to achieve that is this operation called Kronecker product. And yeah, by sort of nesting Kronecker product, you can build up these nice failure fractal like structures. And so this was just an idea I was playing around with, and I was thinking about the kind of infinite limit of something like this. But you get these pretty interesting sort of graphs, and these actually on the plane I was doing them by hand with pen and paper in this pad, because I was kind of so taken by the idea that I was like, okay, what? And it's just like a way of passing the time on the flight.
Sorry, I missed it.
Oh, no. I was just doing it by hand and like, yeah.
I used to do self-automata by hand.
Nice.
Yeah.
That's when, yeah.
Can you show it again so I can stream it?
Oh, yeah. Oh, sure.
Full screen.
Okay, yeah. I was just like taking the individual graphs and then doing the Kronecker product, and then you end up with, the structure of A with the fine structure of B, for example. And there's a few papers where they apply this technique to modeling graphs, sparse graphs with self-similarity. And yeah, it opens up a whole bunch of interesting discussions about irreducibility and blah, blah, blah. There's a lot of things we could go down. But so this was more of a thought experiment rather than let's actually do it, or let's try and fit some of these to causal graphs that we finite causal graphs that we do have. But yeah, I want to think a bit more about the infinite limit of something like this, and
yes,
and
that's what I was asked about. Yeah, right, exactly.
But because actually it came up in one paper on graphons where they do make a what do you call, I forget the name of this fractal, the boxy one, but they do this and they show that it actually converges to the empty. I forget. Yeah, it converges this. Yeah, yes, right. Yeah, Mentor sponge. It converges to the empty graphon actually. But yeah. So again, we've been shot in the foot by infinity. It's like it looks like we're getting somewhere.
That's what I was going to ask about.
It's like, yeah. But the guy makes some modifications to the function and gets it to converge so that it doesn't converge to the empty graphon. But
I think if your fractal has measure 0, then it's gonna normally converge to empty graphon. And I presume this guy did is just take it like, how is it called, like free counter set or something like that. There's when you don't. Yeah, you just cut out less and less at each step of counter set, and you end up with non-zero measure.
That's a cool trick. Yeah, that sounds familiar. I still have the paper. I have like so many tabs that I need to dump into our chat, and we can all look at them.
More dumps, good.
Yeah, and so that was kind of that. And I do want to. Sorry.
Sorry, one more question about this. I mean, the array plots, of course, are cool, but Nick, I mean, would we actually ever expect to generate causal graphs that have this behavior?
I don't think so. No, well, I don't. We can think about it.
This is the adjacency matrix of a causal graph for a rewriting system, and although it's not exactly like that, you could construct this with similar techniques. Maybe not exactly, or maybe up to some degree of error, but I mean, it's undeniable that self-similarity is there. And I know it's also, so these are causal graphs for Wolfram models. actually a lot of the time I couldn't produce anything as interesting as the string rewriting case. But again, there's a lot of interesting fine structure, and then there's this weird sort of this kind of zigzaggy behavior. These I have done a topological sort, but it didn't actually end up making much difference, or it made them less interpretable. And again, you have, I mean, this converge to the identity or just slightly off identity. I'm not sure.
By the way, I wanna bring to attention Jonathan paper, the recent paper by Jonathan about, well, it's about entropy of causal graphs and so on, but it has a nice exposition and review of all the causal set literature and how they associate causal graph adjacency matrix, which is called causal matrix, to propagators.
Nice.
Like to the Feynman
Sounds
propagator.
very.
So basically, this one, the causal graph adjacency matrix of this Wolfram model is basically a propagator up to some constant. And then you can actually make some other functions out of it, do some spectral analysis, and define entropy out of
it. Nice.
So it's very
That sounds very
well done.
Mm-hmm. Yeah, it sounds similar to what we were looking at with the von Neumann entropy measures and things like that. Let's see, and the operator parent Frobenius. So let me see. I don't want to miss any of these. So we've got enumerate. Oh yeah, enumerate was this is the notebook that loves to hang, because I enumerated all 2,000 of a particular signature, and as you can see, there's some diversity. Then you have these regions where there's not so much, but yeah, there's a large family, family of different motifs that just randomly calculate layout again. So it sits there for ages, and my computer fan goes fast. Anyway, these are the corresponding adjacency matrices for those. You can see some of them terminate earlier, some of them are still going. This is more sort of exploratory, less theoretic. I just wanted to take an actual look at different systems, and I've also got cellular automata as well.
What was those causal graphs that you just showed?
Yeah,
they were causal graphs of what kind of?
Wolfram models,
okay.
And I just enumerated like a given signature completely. So I think it's about 2,000 different things, and what I was going to do was just turn this into some training set for one of the methods that we had discussed.
Yeah.
To actually apply it in the machine learning setting. But
for purposes of, I'll just say one thing. I mean, you probably know this, but I'll just say anyway. For purposes of efficiency, one, you probably don't actually need to render all the causal graphs, and you could probably just get the isomorphism classes and just get the matrices for those. So like in this case, for instance, I imagine there's a streamlined version where you probably get 10 matrices, maybe, or 10 to 20 matrices, and they're just the matrices for the isomorphism classes. And then you're it would be much shorter. So as you scale this, you probably want to do something like that, right?
Well, I mean, actually, in general, what would be nice to do would be some kind of decomposition, which gives you some sort of basis from which you can build all of them. And that, in a sense, would give us a space in which we can sort of move around, but not every point in that space would be a valid causal graph, if you see what I mean. So we would extract some kind of basis matrices, and then combinations of those would give us these causal graphs. But we raised
that's an important point, because like if we could take arbitrary grounds, for instance, this would just reduce to the moduli space of graphons problem, but it's not that, right? Because so
we want every point in space to correspond to a different computational system. A different because you abstracted away the initial state and the rule, so it's both of those together. So edit distance was something we discussed in the finite and infinite case, and I believe Łukasz mentioned it, and I was thinking about it still. So I've actually taken. I couldn't find any functionality to compute graph edit distance in Mathematica, so I today hooked together just this stuff here, which gives us it hooks into this Python package network X. And Nick mentioned he's been doing some Python thing to pass graphs back and forward to Python. So this one gives us a normalized graph edit distance or an unnormalized graph edit distance. When it's normalized, we normalize against the number of graph node plus edges and take the maximum of that. So we get some number between 0 and 1. Normalized just gives you the number of operations you need to perform to get from one graph to the other. And this is quite slow because it's...
How's the edit graph is defined? Like
I mean, these are just like,
removing
removing vertex, adding an edge, just those basic atomic operations on the graph. Yeah.
Are they events?
No. So we can't really think of them as such. What we're trying to do is compute a distance metric between causal graphs outside of anything to do with causality or whatever. We're just taking a sort of the equivalent of Levenshtein distance or something like that between two graphs, with the idea.
Okay.
Sorry.
Okay.
Well, with the idea being
some graph intersection, graph difference combination. If you just removing an edge and adding an edge.
Not quite, because there is a sort of search problem. One has to search over all the options to get the sort of minimum edit distance between two graphs. They may not intersect. Like, for example, let me see. Like, two graphs might have some intersection, but large amounts of non-intersection. And there's also completely disjoint graphs, or, well,
it also I don't graph sub isomorphism, right? So you allow it also to map vertices into each other, right?
Yeah, I mean, if you did compute the graph intersection, maybe that works. I mean, that's perhaps even what this network X function is doing, but it's quite computationally expensive. And as you can see, it's still so let me just explain what I've been doing, and then we can figure out if there's a more efficient way of doing this. So the idea being that we try and approach the graph realization problem, which is given a bunch of edge lengths, can we embed the graph in some d-dimensional space? So if we compute so each vertex here is a causal graph, and if we know the distance, the edit distance between causal graph, A and B, we can enforce that edge length, and not try and embed this in the plane or 3, 4, or 5 dimensions or something, and then that gives us, or at least moves us in the direction of approaching this idea of moduli space. Does that make sense? So actually, these are all causal graphs of cellular automata, all 256 of them. Again, I've gone to town with plotting all of them, and then what I've done is now it's in the middle. I've just taken a bunch of subsets from this pool of causal graphs, and I'm computing the pairwise edit distance between them.
Sorry, Richard, can you say one more time?
Yeah.
What role will the edit distance play in understanding the moduli space?
So if we have like 3 causal graphs which are one edit away from each other, then we know that they exist on an equilateral triangle in the moduli space. And if for example 2 of them have edit distance 2 operations or something, then we have a that kind of triangle, not an equilateral triangle. Does that make sense? So if we know the pairwise distance between all causal graphs versus every other in the set, then we can do this graph realization problem to sort of embed that into space.
Okay.
Make sense? Yeah. And we can do that for the finite case, and then start looking at the limits as we start growing this, which I think is getting more towards what Łukasz was saying, but in a much more simple-minded way, because it's from me.
One quick question, Richard. So
make like some kind of feature space plot. You can even do multi-dimensional scaling algorithm, because it's just linear matrix multiplication. If you have a distance matrix between your causal graphs, you can immediately do some linear algebra and come up with some nice embedding for each of the causal graphs, so that they can put it into some higher dimensional space.
Right. I mean, that's why I was looking at the graph autoencoder idea, which was, take the adjacency matrix, some convolutions over it to reduce it down to some vector, and then use something like t-SNE, which is like a nonlinear embedding, and then you'll get that nice feature space. I mean, I'm sure Mathematica has probably built in this t-SNE, which is like quite a common.
But I would just look at the linear one.
Right.
But the thing that you extract from just the distance matrix between your object, in this case causal graph, just give.
But I mean, aside from visualization,
the algorithm is multidimensional scale. There's some resource functions.
And that applies even if I only have some kind of single scalar metric between them, because in this case I do with this edit distance. So that's why I'm looking at the graph realization as a way of like visualizing this. But obviously, not all graphs embed in the plane, so or in 3 dimensions. So you have to go to higher and higher dimensions. But who's to say our moduli space has to be 2D? I mean,
no, we don't know what it looks like. That's
exactly
that's the problem.
But
if we knew, we could publish. It would be over.
So here is
one quick request, by the way. So you're producing a lot of notebooks, and we discussed, the last time we chatted about this, there are a number of different approaches that can be taken at this early stage, and we're not exactly sure which will be helpful, et cetera. Keeping track of all these ideas. Maybe if you have a notebook, I don't know how you want to do it. Basically, either if you have a notebook and the notebook is being created to pursue some particular idea or plan that we've discussed, writing like a sentence or two about it, keeping some record somewhere, because I worry, just given the rate at which you're producing these notebooks, it's going to be hard for me to go back and look at them. And I also just worry about us keeping track of all of the ideas that we're generating.
I think it's very easy for ideas to get lost in the noise, I think,
or just for ideas to get lost in the ideas.
One idea would be like a folder per sort of concept, and then you have a main notebook which is mostly textual, and then other notebooks are your work in progress, and then you sort of pull concrete results back into that sort of master document or whatever. So you can have anyway. Anyway, so this was just an example of like 2 graphs, and then your edit distance of 2, or normalized edit distance of 2.5. It just gives you a nice scalar, and then the idea was with a set of those, we would be able to then show our moduli space as something like this. Something like Spring electrical embedding is only. It's only able to solve the graph realization problem up to some extent, because it depends on how the vertices were initialized. It depends on if the graph can even embed in the plane. We know that not all graphs can, because you can create some paradoxical situations. Anyway, that's another idea I was looking to explore.
Let's just discuss how we would use this ultimately. So you can imagine creating a kind of an embedding based on this distance, even for small graphs, causal graphs like these little baby ones. It's not. Sorry?
For cellular automata, these are.
Okay. That's not surprising. Okay. What was I gonna say? Yes, I mean, it's not.
Cyclic, by the way.
I think because I wondered that as well, but I think because the state space is so small that it
is the I don't know what you want to call it in a Turing machine term. We just call it the tape. Is it bounded?
I think so. It's bounded.
If it's bounded, these things roll over themselves all the time.
The Poincare recurrence time is low for these universes.
Canonicalization of those events is not perfect, basically. There has to be some, step number addition to those events in order to distinguish them. Events shouldn't be canonicalized in this.
The reason I did this is it's much faster to get these than to enumerate all hypergraph rule. That takes time, so it's just a way of getting something so that can feed into the functions below, and then we can apply them to, proper stuff.
Yes, I mean, Nick is raising an important point, which is we have to have some standard way of reducing the causal graphs that makes sense. Like if some of them are canonicalized and some of them are not canonical, and some of them have all these loops because we're not, then this won't, we have to have some standard way of producing isomorphism classes, obviously.
Right. Okay.
Now, my question about these graphs, though, is, I mean, there are a few things we could do, especially for the Institute report, as we've discussed before, right? Even kind of, expository graphics, for instance, that show for the finite case how you could start to consider a space of isomorphism classes of little small graphs. That in its own right, as an expository exercise, not useless. My question is, in terms of this graph edit distance, unless wrong, which can happen, I'm presuming that this is not something that you consider in the limit. Do you consider this in the limit? Would you do this for graphons?
I think well, there is a notion for graphons. It's called the cut metric, which I raised previously.
Right, you mentioned this.
Yeah, and it, obviously involves some integral and whatever over your two. If you're comparing two of these functions, then you do some integral involving both of those functions over the domain of both of those functions. And
right, but it's different from this edit metric. So my question is, how would this edit metric be used?
Well, this converges to the cut metric, I believe.
Okay.
So,
so we could use it, strictly speaking, we could use it as an illustration of this is what it looks like when the graphs are finite and small little graphs, and then this limits to the cut metric. Okay, that's perfectly fine.
And that's why I'm exploring the edit distance also, and we can speak about both cases. And also, I think Łukasz did, unless I'm putting words in his mouth, I think Łukasz did mention when he was discussing this non-standard treatment, I think he mentioned something about some form of edit distance or something like that. But I'm not sure if I'm putting words in your mouth. But
well, let's let Łukasz put words in his own mouth.
When you were discussing.
So once again, what you claim I mentioned?
I thought you mentioned something about like some sort of distance metric between these limiting graphs and it being something related to edit distance. But I don't remember exactly. And it was when we were having this discussion about ultrafilters and non-standard analysis and so forth.
Do we have it recorded somewhere, or
possibly?
I might have an internal recording of that.
I don't really remember, or in what context they was saying.
Yeah, I think we are building up things on both the finite and infinite case, and I think the sparsity and the sort of complications involved in modeling these things is the big challenge now.
I have a question. So I remember when we discussed this before, we considered two kinds of approaches, right? One is you actually run computations, and then you get the causal graph. The other one, which is completely different, is you take a manifold and you do some sprinkling, and you had kind of suggested last time that you think the sprinkling could be especially a helpful kind of short-term approach because you think it might, at least at the time, you thought that it might be easier to get things like graphons once we begin with the manifold and we do the sprinkling, because you can much more readily reach that.
And these kinds of densities these functions are much easier to fit. And to be honest, that's why I've now started to approach the difficult things, because I know that this is trivial. So we've made some headway on this, and it's like, let's now start pushing the other aspects of this problem because if I take a sampling of these manifolds over some domain of these exponents or something, and then try and fit some multivariable function with these, I mean, I can do that in a matter of hours or something.
Do it.
Yeah, absolutely.
I mean,
I will. But
this is like this is almost like an inside joke between Nick and I at this point, where Nick will say things like, "Oh, I didn't do it because it's so obvious and easy that it's
no.
We can do it some other time." But
it's more just like I wanted to shift to other things, and yeah, I mean, I will pick this up. Yeah,
you never know. I mean, I don't know. It could be that 2 steps from now something really difficult happens. So always there's some saying from Steven, like basically just go for the hard part, the difficult part, basically as soon as you can.
I mean, the other is we just, a more sort of general thing was the machine learning approach, because that would kind of cover these manifolds and the computational case. But it's only up to the power of these models to sort of embed that space of graphs in some sort of meaningful latent space, and a lot of that is very empirical, and it's not really principled in a sense. You're just like, how many neurons do we choose? What are the parameters in our loss function? How do we tune those in such ways to, it's a very kind of ad hoc kind of empirical thing. Although it does have principles, it's not, whereas something like this problem, it's like, yeah, we just choose some, I don't know, some function signature polynomials or whatever, and then do some simple regression. Bless you, whoever that was. Somebody sneezed.
Bukash.
The camera stayed still, so I was like, who was that?
Yeah, it's in the room.
Okay. Bless you, somebody. But yeah, I will. Yeah, I'll make sure I push this one a bit. This nice graph that, up to as good as the embedding has managed to position the vertices, we will have. Actually, if the vertices are in high dimension, I think we can apply what Nick's suggestion of these high dimensional feature space plots, even to the vertex positions in some high dimensional space. So embed the graph in n dimensions, and then do this do these linear or non-linear embeddings.
Well, in terms of progress, this is of course great. I mean, this is the first meeting, we have like 7 notebooks. My main concern is just that this project itself is already quite multi-way. Like there are many frontiers along which it's being pushed, and yeah, my main concern is it's not really keeping track of them. It's having a self-aware strategic understanding of the contribution that each particular approach is being the contribution that each one will offer. And like, some of these will be, well, we're going to try both of these and we're going to kind of compare them, and we'll ultimately pick one. Or one of, some of them will be, we want to do this over the short term, and we think that this will be helpful as an exercise or even as a precedent for another. So like sprinkling, sprinkling can be done easy over the short term. This should be able to help us when we do the generative case as opposed to the sprinkling case. We have ones where we're basically just studying behavior, like this one, and this is helpful for basically computational experiments. And I will say, I love people talk about interdisciplinary research, but this is a combination of pure math, computational experiments, machine learning. Yeah, I mean, I don't know of that many projects that are like that. So it's pretty cool.
It was definitely very interesting and fun to work on. So yeah, it's
good.
Yeah.
Well, oh wow, it's already been an hour. Did we look at all the notebooks, by the way?
Yeah, I think we did. Yeah,
Okay.
we covered most of them.
Are you able, Richard, to summarize all the different things that you've said that you're going to do in the course of this live stream? Because there are a few of them. There are like 5 or so.
Let's try and do it in like 1 or 2 sentences. So we're looking at,
here we go,
taking infinite limits of graphs and modeling those to form a continuous space in which we can explore these causal graphs. That we've bumped into some tricky aspects of our causal graphs, which is that they have a lot of sparsity and a lot of irreducible complexity that we have to find, other methods of modeling, whether it be, these chronic, or we take an approach where we look at, say, graph edit distances and we construct our space in this manner. Additionally, there's these machine learning variational autoencoder type approaches, which would get us to the same place, but through different means. So yeah, we're building the tools. Once I can export some of these graphs and actually sort of train, because it's more flexible using machine learning toolkits sort of outside of Mathematica at the moment, at least for me anyway. So once I get there, we shall actually have some models where we can put causal graphs into, and we can locate them in this latent space, which is our sort of like placeholder for the model. But yeah.
Okay. Well, this is coming along well. Maybe we can have another meeting later this week and check in on this. Yeah. All right. Well, good initial meeting. I think I have a call with some of you guys in like half an hour, 20 minutes or so. All right. Well, thank you, Nick, for hosting the stream. Hopefully there's been audio this whole time. My God. Hopefully. Anyway, there's
some issues in the beginning. Not just audio, but I think it's okay. I think our stream crashed or something. Well, I don't know. At some point.
What do you mean you don't know?
I mean, the stream, or
did it crash? Did it crash?
Discontinued for a little.
For how long?
It was on a restream site. I don't know, maybe a minute or 2, and only on YouTube. But I don't know. It just showed that it's not streaming on YouTube.
Well, audience members, future viewers, sorry about this. I'm not sure if it's Nick's setup or what. We usually don't have these problems with Carlos, or maybe Carlos isn't saying anything about that. I don't know. Anyway, we're learning how to stream. Anyway, hopefully the parts that you saw, which you liked, and hopefully you saw the majority of it. I'll take a look at the recording at the end, and we'll fix these bugs. All right. Anyway, Richard, yeah, well done. This is a promising start. And yes, Łukasz and Richard are doing some sort of exchange program between Central Europe and the UK. So they've traded split. Can't wait until Nick and I both do that. Anyway, all right, guys. See you later. Cheers. Bye-bye.
Thanks. Bye-bye. Cheers.
Bye.